Hi everyone, today I'm going to talk about light. So light, before we can talk about light, we're going to talk about electromagnetic radiation. And so first we'll discuss light as an electromagnetic wave. Okay, electromagnetic radiation or waves. So waves have a frequency. We use this Greek symbol, looks like a V for frequency. And then this funny looking Greek symbol we're going to use for wavelength. Okay, c is equal to the speed of light, which is 3 times 10 to the 8th meters per second. We'll be using this equation in the honors class. If you're in the regular class, you don't have to worry about this equation. So light as a wave, so a wavelength is from one crest to another crest. It could also be one trough to another trough. And then the frequency is how often it goes through one cycle. So that's one cycle, and then this would be another cycle. Okay, the electromagnetic spectrum is made of many different kinds of waves, but in general, if you've got a long wavelength, that means a smaller frequency, and if you've got a short wavelength, that means high frequency. So what does high frequency look like? Just look at this wave on top. You can see that this wave has a high frequency. It goes through many different cycles. Okay, versus low frequency, notice there are much less cycles. So when we look at the visible light spectrum, we'll see that red waves tend to be low frequency and larger wavelength. And then violet waves tend to have the opposite, high frequency, shorter wavelengths. So here we can see many different kinds of waves, not just the visible light spectrum. So the visible light spectrum is a small part of the entire electromagnetic spectrum. You'll learn more about it, but it includes radio waves, microwaves, infrared, UV rays, that's why we wear sunblock, X-ray, and gamma rays. So as you go to the right, this is going to be higher frequency. And higher frequency means shorter wavelengths. Okay, on the opposite side, we have the opposite. We can see here, this is going to be longer wavelength, and that's going to be lower frequency. Okay, so be sure to check and review the electromagnetic spectrum. In terms of the visible light spectrum, if you're trying to remember the order, red, orange, yellow, green, blue, indigo, violet, or Roy G. Biv. So red's going to have the longer wavelengths, and then violet would have the shorter wavelengths. Why is the sky blue? You're going to watch a video that explains why the sky is blue and why we see beautiful sunsets like this photo that I took.
Why is the sky blue?
Well, the quick explanation of why the sky is blue is because of how light from the sun interacts with the Earth's atmosphere. But to really explain this, we need to know a bit more about light itself. The white light from our sun is actually made up of a whole range of different colours, which we see for ourselves when we see a rainbow in the sky. Scientists call this rainbow a spectrum. Each of these colours has a slightly different wavelength. Red light has the longest wavelength we can see, while the wavelength of blue light is much shorter. So how does this all tie into the colour of our sky? The secret is in how the light reacts to the gases that make up our atmosphere, mainly nitrogen and oxygen. The molecules of these gases interfere with the incoming sunlight. The short wavelength blue light is more strongly affected and is scattered in all directions, while the longer wavelength green and red light is able to pass straight through. As you look at the sky, you're seeing this scattered light, and so the sky looks blue. So, if the atmosphere scatters blue light more effectively than red light, then you may wonder why sunsets look red. The answer's twofold. Firstly, when you look at the sunset, you're looking toward the sun, not away from it. So while the blue light has been scattered away, you're looking at the redder light that passes straight through the atmosphere to your eyes. Secondly, the sun is low in the sky, and so the light is forced to travel through much more of the atmosphere than it does at midday. In the process, it passes through far more water vapour and dust. Water vapour and dust both absorb the short wavelength blue light, while letting the longer wavelength red light pass straight through to your eyes. Astronomers are using the principle of absorption to study the atmospheres of planets around stars many light years away. Different molecules absorb different wavelengths of light, making a unique pattern in the spectrum, like a fingerprint that we can use to identify the molecules. By identifying these fingerprints in the light from distant worlds, we can even tell what the atmospheres are made of, even from billions of miles away. Using the Spitzer and Hubble space telescopes, astronomers have been able to use this technique to find clouds of sandy dust in the atmosphere of one Jupiter-like planet called HD 209458b, along with sodium, oxygen, hydrogen and carbon. The hope is that someday soon we may even be able to tell whether a distant planet has life or not, just by looking at its spectrum.
So we talked about light as a wave. Next, we're going to talk about light as a stream of particles. So light as particles, light bounces off objects like a particle, and it travels in bundles called photons. So how did they figure this out? Basically, they shined a light on a piece of metal, and they found that they could eject electrons if the light was strong enough. Okay, so if it was just a wave, then any frequency would remove an electron, but because light behaves like a particle, they needed a high enough frequency to remove that electron. In my honors class, we'll go over this more. Okay, so this is going to be important. We're going to talk about how light is produced, and we'll use two slides here. So when an atom absorbs energy, light, or photons, its electrons move away from the nucleus. So we start in the ground state, which is low energy. And then we're going to move to the excited state. So after it absorbs energy, the electron moves to this excited state, as you can see here. So closer to the nucleus equals lower energy, and we're moving from the ground to the excited state. So at this point, no light has been produced yet. Our atom has simply absorbed some energy to get to the excited state. So once it's in the excited state, it's when it goes back down into the ground state. So excited into the ground state. That's when we're going to see a release of energy or light. So this is what we see as light. So this energy or light is proportional to the energy or light that it absorbed. So for example, if it absorbed a green wavelength, it's going to release a green light. If it absorbed a red wavelength, then the wavelength that comes out is also going to be red. So I'm going to show you a little animation that demonstrates this. Alright, so here is a little animation showing you that whatever energy that an atom absorbs, right, it's going to release that same kind of energy. So here I've got a red wavelength on my hydrogen atom, and it's going to absorb that red energy. So pay attention to the electron floating around here. Okay, so there you saw a red energy hit. It went from the ground state to the excited state. And then when it falls back down to the ground state, it's going to release that same kind of energy. So in this case, it's going to be a red wavelength. So check this out. Okay, so again, in case you missed it, it's going to absorb a red wavelength and then get into the excited state. And then when it goes back down to the ground state, this is when light is produced. and it's going to release that same kind of energy, in this case, red. Lastly, electrons can be on different energy levels, but it can never be between energy levels. Basically, the move is instantaneous, so you'll never see an electron hanging out between energy levels.